In this example, I will go ahead and use SimXpert to analyze the bending stress of this cross-section shown here with this given load and the given dimensions. Ultimately, we are to get 4 bending stresses, 2 in tension and 2 in compression. So I will go ahead and define this in SimXpert. I'll switch over, click on structures. Now to model this, I will create a beam that is 3 meters in length. So I'll go ahead and first create, or before that, I have to save this to a directory. So I'll select a folder on my desktop, and I'll call this bending 2. For my units, I will use meters, kilograms, newtons. Click OK there. Let's save again just to be sure. Now to define my geometry, under this tab I go and create 2 points. One defining my root and another one defining my free end. So it's 3 meters in the X, 0 in the Y, and 0 in the Z. Hit enter one time to preview the points and hit enter again to confirm the creation of the points. Now I want to view this such that my X is in the horizontal and Y is in the vertical, so I switch to the top view here. Now to create my curve, under curve from points, I'll select auto apply. Simply click this point, and after I click this last second point, it automatically creates my curve. Click cancel. Go to the meshing tab, under auto mesh, click curve, select this one curve, and click OK. Now when I turn on my ID displays, I see 10 elements have been defined. I then move over to my materials and properties tab. So before I do that, let me expand my model browser tree. Here under isotropic, I define my material. I'll leave the name as ISO1. My Young's modulus will be 70e to the 9 pascals. My Poisson's ratio will be 0.3. Now I click OK. I define my beam section. Here we're using a bar. And if you recall from the problem, we have, in this example, I will define it in such a way that the Y element axis coincides with the global Y axis. So here my depth or height is 0.4 meters and my width is 0.2 meters. So my height or depth is 0.4 meters and my width is 0.2 meters. 0.4 again and 0.2 here. So my width and my height. Now I click OK. I'll click apply and leave this open. To create my beam property, right now we just create a cross section. I'll click beam here, it opens the beam property form. I'll select cross section type as one defined in my library. For material, I'll pick the one material I just defined right now. For section name, I'll define or specify the beam section I just created or the cross section I just created. For entities, I'll select all the elements. So let me uncheck these and click all. Selects all the elements. Under apply elemental data, one very important part is my orientation vector. So let me reorient the model. I said I was going to define this in such a way that my Y element axis coincides with the global Y axis. To do this, you simply defined an orientation vector that is 0 in the X, 1 in the Y, and 0 in the Z. And remember, my X element axis is running into the plane here. Since my elements are running in this direction, my X element axis will be running down this direction. Since my orientation vector is in the global Y here, the y element axis will now be in the global y, and my z element axis will be coinciding with the z element or z global axis. Let me verify these, and now I click OK. I can cancel out of this. Let me turn on detail rendering. And now you can see the height is in the global y and the width is in the global z. And one last comment. Remember that this point here is C, D, E, and F. And this is important when we go ahead and review our results. So here we have point C. Let's see if I can clean this up a little. Point C here. Point C, D, E, and F. If I were to rotate this, that would be C, D, E, and F. But let me just stick to this orientation. C, D, E, F. Let me go ahead and define my LBCs. Turn this off. Define a fixed condition at this node. Node 10, click OK. For my moment, I select this node. And from the problem statement, it's 7.2 in the z direction and negative 9.6 in the y direction. So I'll leave that as a scale factor of 1. For my y, it's negative 9.6 e to the 3 and 7.2 e to the 3. So I click OK. And let me turn on my 3D LBC marker. So let me reorient this axis so it sort of looks like the same orientation as in the book. Turn detail rendering on. So now if you look at the example, the figure resembles this figure here. And I think I'll go ahead and leave it like this. And before I go on, I want to remind everyone that this is point C, D, E, and F. So when I rotate this, this is point C, D, E, and F. Let me go ahead and go to File Set, create new Nastran job, call this Bending 2. Navigate to the folder on my desktop, save it here, click OK. And like I did in the previous example, I'll output grid point force balance so I can view my free body diagram later on. So now I can go ahead and run this job. Let me go ahead and turn off 3D LBC marker. Let me turn off the IDs and detail display. Now I'll turn on 3D beam section. So one quick reminder, in this example, my y element axis coincides with the global y axis, and that is because my orientation vector is defined 0 in the x, 0 in the z, and 1 in the y. Since my elements are running in this direction, again starting from here and on, since this is the direction my elements are running, this is my x element axis, so my y element axis is in this direction and my z element axis is in this direction. I'll go ahead and attach my results. Here I have my XDB file. Click OK. Results have been successfully attached. Let me keep this view. So when I go to results and click a fringe, we'll now compare it to our actual results or analytical results. So point C, we should get a compressive stress of 4.95 megapascals. So let me switch to bar stresses bending here, point C and the X, and click update. You'll see if I can get this in the view. And since there's only a moment applied to this beam, you'll have just bending stress throughout the length of the beam. We do get negative 4.95 megapascals, and negative indicating it's in compression. Now point D here is negative 2.25 megapascals. So when I do that and click update, I get negative 2.25 megapascals. Again, this is in compression because of the negative sign. For point E, you get positive 4.95 megapascals. So point E is 4.95. And for F, it's 2.25 megapascals. It's in tension. And here, the book doesn't use the same convention here, but for point B, they get 2.25. In our convention, point F, we get 2.25. Let me hide this. To view my free body diagram, I can click free body here, or here under type, I can click and find free body here. And when I select free body diagram and click update, I can see my free body diagram here. And here you'll see, let me turn all of this off. You'll see my two moments applied, my 7.2 kilonewton meters and my 9.6 kilonewton meters. And these are the two moments here. So that's one additional check you can do if you begin doubting your results. Remember to save, and that concludes this example.